Hello friends, welcome to the 17th class of this course. In the last few classes, we were doing some applications of Lagrange's equation of motion and the variational principle. In the last two classes, we did some very interesting problems, and most of the problems were from Spiegel, the theoretical mechanics book by Spiegel, and a few of them from Goldstein. So today we will do three problems, and all of them will be from Goldstein. So let's start. So problem 6. The problem statement is, show that Lagrange's equations of the form of ddt of del t del qj dot minus del t del qj equals to qj, and here the qj is generalized force. And T, this T is kinetic energy, and Qj are the generalized coordinate. So we already saw that Lagrange's equation that can also be written in this form. Actually, from this form we derive the Lagrange's equation, the standard Lagrange's equation that we know, that is ddt of del L del Q dot minus del L del Q del Qj equals to 0, where L is T minus V. So if the Lagrange's equation is written in this form, then we need to show that this form can also be written as, this Lagrange's equation can also be written as del T dot del Q j dot minus 2 del T del Qj equals to Qj. And this form is also known as Nielsen equation, Nielsen form of Lagrange's equation. So basically what we need to show is this ddt of del L del Qj dot minus del T del Qj, it equals to del T dot del Qj dot minus 2 times del T del Qj. That's what we need to show. So if we can show that these two terms are equal, then it follows from this equation to this Nielsen equation. Solution. This kinetic energy, it is basically function of q1, q2 dot 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 qn, comma q1 dot, comma q2 dot, comma dot 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 qn dot minus t. So now So here, if we calculate ddt of del t del qj dot, it will be, so if we calculate ddt of del t del qj dot, it will be, so this del t del qj dot, it also depends on qj's, that means q1 q2 dot qn, and qj dots, that is q1 dot q2 dot q dot qn dot, and time. So in that case, the ddt of del t del qj dot, it will be sum over k del qk of del t del qj dot qk dot plus sum over k del qk dot del t del qj dot qk double dot plus del t of del t del qj dot, right? So let's call it equation 1. Now let's calculate this term, this del t dot by del qj dot. So del t dot by del qj dot equals to del qj dot of t dot. T dot means d capital T by d small t. Sorry, it's not del, it's d. Right? It means del qj dot of sum over k del t del qk dot del qk del qk dot plus sum over k del t del qk dot qk double dot plus del t del small t. Now if we take the derivative, we will get this del qj dot, it will be, so it will be sum over k del t del qk del qk dot by del qj dot plus sum over k del 2t del qj dot del qk dot plus, so this del qj dot of this term, so it will be derivative of, so first this term intact, derivative of this term, which is this one, del qk dot by del qj dot, and then this term intact and derivative of the first term. Okay, it's the derivative of summation of multiplication of two functions. And for and derivative of this term, it will be sum over k del t del qk dot del qk double dot del qj dot plus sum over k del 2t by del qj dot del qk dot times qk double dot plus del 2t del qj dot del t. So now this term This term is delta of k comma j, and we already know what is this delta function. This delta of k comma j means when k equals to j, it is 1, and when k not is equals to j, it is 0. Because qj and qk, they all are independent. Qj's are independent. So only del qj del qj dot del qj dot, that will be 1, and if j not is equal to k, then the derivative is 0. So here this qk double dot, these are independents of qj dots. So in that case, it will be 0. So like q's, these are independent of q dots, and q dots, they are independent of q double dots. Okay. So in that case, we will get from the first term, we will get sum over k del t del qk delta of k comma j plus sum over k del 2t del qk del qj dot. So we are interchanging these two terms because partial derivative, they are commutative. We can interchange them, right? And this means del qk of del t del qj dot. So we can write it this way also. It means del qk of del t del qj dot times qk dot plus. So this term is 0, and this term we can write it like sum over del qk dot del t del qj dot times qk double dot. There also we are using that the partial derivative, we can interchange them. Plus here also del t of del t del qj dot. Now from equation 1, we can recognize easily that these three terms, these last three terms, it is basically ddt of del t del qj dot. Just look carefully. All these three terms, these are here, these three terms. So we can write it as, so this del t dot del qj dot, del t dot del qj dot, del t dot del qj dot equals to, now this summation, as there is a delta function, so we can write it as del qj, del t del qj plus, and these three terms, sum over these three terms, it is basically from equation 1, we can write ddt of del t del qj dot, ddt of del t del qj dot. Then if we subtract by twice del t del qj from both sides, we will get del t dot del qj dot minus 2 del t del qj equals to ddt of del t del qj dot minus del t del qj. So we are almost done. So we got this right hand side. So this right hand side is this term, and this term equals to the right hand side of this Nielsen equation. So this Nielsen form, right? This term. So then from the given form of Lagrangian equation, we can write using, sorry, using equation 2 from the given form of Nielsen equation, we can write, from the given form of Lagrange's equation, we can write del T dot del Qj dot minus 2i's del T del Qj equals to Qj. Which is the required Nielsen form. Okay. So this was our problem 6. Now let's do the next problem. Problem 7. The problem statement is the electromagnetic field is invariant under gauge transformation. Gauge transformation is a transformation of the potentials. The potentials are not unique. By gauge transformation, we can redefine a new potential, keeping the fields as it is, keeping the fields invariant. So that's the gauge transformation. So the electromagnetic field is invariant under gauge transformation of the scalar and vector potential of the scalar and vector potential given by A to A plus divergence of psi r t. Psi is any differentiable function of r and t. So A can be, the vector potential can be changed by this gauge transformation in this way. So, and the scalar potential, we can redefine it like minus del psi is a function of r and t del t. So we can change these potentials, so the scalar and vector potentials, and define it in this new way by using the psi, which is a differentiable function of r and t, but the electric fields will be intact. Where psi is any differentiable function or scalar. Now the question is, what is the effect of this gauge transformation on the Lagrangian? Is it changing the Lagrangian? On Lagrangian. And the next question is whether it is changing the Lagrangian equation of motion or not. What is the effect on Lagrange's equation of motion? Let's solve this. So we know that if A is a vector potential and phi is the scalar potential, then the Lagrangian is defined like half mv square minus q times the scalar potential plus q a dot vector potential, a dot v. A is the vector potential and v is the velocity of the particle. So now our new scalar and vector potentials, they are defined as the new scalar potential. Let's define it by phi tilde. It is defined like phi minus del psi del t. The psi is a differential function of r and t, and a tilde, it is defined as a plus divergence of psi of rt. This phi tilde and a tilde, these are the new potentials, redefined potentials. A is a vector, so let's put a vector sign here and tilde. So if these are the potentials, these are the new potentials, then our new Lagrangian will be, let's define it by L tilde, it will be half m v square minus q phi tilde plus q a tilde dot b. Now we will replace this phi tilde by this equation and this a tilde by this equation. Then we will get minus q phi, and we will write this term after writing this q a dot v. Okay, so from the first term of this equation, we will get q a dot v, and then we will get plus q times del psi del t, and plus q times divergence of psi dot v. Okay, so this is the previous Lagrangian we had before the transformation. This is the Lagrangian we had. So this is the L. So we have L plus Q, or we can take the Q inside. We will get del del T of Q psi plus sum over K del del QK Q psi times QK dot. It is the second term. So if we write it in terms of generalized coordinate, it will be like this. So here this QKs are the generalized coordinates, and this Q is the electric charge. Okay. So don't be confused by this Q. This Q is electric charge. So this term, if you can recognize, this is ddt of Q psi. where psi is a function of R and T, and Q is a constant electric charge. For a particular charge, it is constant. So then our new Lagrangian L tilde, it will be L plus ddt of, let's say, F, which is a function of R and T, where F, it is not a vector, F is Q psi. So this will be our new Lagrangian. So with the gauge transformation, Lagrangian is not invariant. It is changing. But what about the Lagrangian equation of motion? Because that's the equations that captures the motion of the particle, right? That's the equation of motion of a particle. We already know, we already solved a problem which says that if we add this kind of term like dfdt, where f is a function of r and t, if we add this kind of terms with our Lagrangian, the Lagrangian is invariant. So we already did this problem in our previous class. So in that case, we can, from there, we can easily conclude that though the Lagrangian is changing, the Lagrangian is changing, but the Lagrangian or Lagrange's equation of motion is not changing or is invariant under gauge transformation. So Lagrange's equation of motion, these are invariant under gauge transformation, because the gauge transformation only adds a term like dfdt, where f is a function of rt, and adding these kind of terms will not change the equation of motion. So we already solved, we already showed in previous class that Lagrangian is not unique. We can always add, this kind of term while keeping the Lagrange's equation intact, invariant. So this was our problem 2. Now let's do another problem, but before that, let's define something. It is called the point transformation. The point transformation is defined as, let q1, q2, dot 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 qn be a set of independent coordinates, generalized coordinates for a system of n degrees of freedom. With Lagrangian L which is a function of q, q dot, and t. Now suppose we are changing, so we are taking a different set of independent coordinates. So basically we are changing the basis. Suppose we transform to another set of independent coordinates, which are s1, s2, dot 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 sn, by means of a linear transformation equation like si equals to si, which is a function of q1, q2, dot 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 qn, t, for all I equals to 1, 2, 3, dot 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 n. This SIs will be function of q1, q2, dot dot qn and time, but it's a linear transformation. That means there will not be terms like q1, q2 multiplied or q1 square or the higher powers of that. Okay, so this is how the transformation is defined. It's a linear transformation. That means if we do this del SI and del qj, it will be a constant. It will be a constant. It will not depend on any other coordinates. That's how this linear transformation is defined. Or del SI del t, if we do. So in that case, the Lagrangian would be L tilde of s dot t. The Lagrangian will now depend on s dot and t. So Lagrangian, this Lagrangian will be same, but its functional form will be different. So which will be same as q dot t, but its functional form will be different. So it will be in terms of this s coordinates. Such a transformation is called point transformation. There is nothing complicated about it. It is just we are changing the basis and we are seeing the Lagrangian with this new basis with respect to the new basis. So now the problem is the thing we need to prove is prove that Lagrangian equation is invariant under point transformation. So we need to prove that under this basis transformation, the Lagrange's equation will be invariant. So now what we have solution, what we have is any sk, let's say it is a function of q1 dot 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 qn comma t, and sk dot, this will be function of q1 dot comma dot 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 qk dot comma t. So in that case, and as the transformation is linear, we will get del sk del qj, and ddt of that, it will be 0, because del sk del qj will be a constant and ddt of that will be 0, because the transformations are linear. So linear means this sk, it will be sum over this qj's, let's say, and some alpha j, where alphas are constant, plus some tau times t. So in that case, if we do the derivative with respect to any qj, any q, it will be a constant if we do a partial derivative. And then if we take the derivative with respect to time, this ddt of sk sqj, it will be 0, right? So this is how the linear transformation is defined. Similarly, ddt of sk dot del sk dot del qj dot equals to 0 also, because this dot, so sk dot, which will be dependent on q1 dot 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 qn dot comma t, this is also a linear transformation. So these two are because of the transformation is linear. The point transformation is linear. And now we have this del L del Q J, it equals to sum over K del L del SK del SK del QJ, and del L del QJ dot, it equals to sum over K del L del SK dot times del SK dot del QK dot. Let's call it equation. So we had equation up to equation 2. So let's call it equation 3. Let's call it equation 3 and equation 4. Now, in terms of q's, the Lagrangian we had, that was ddt of del L del qj dot minus del L del qj equals to 0. This already we know. Now if we transform them, we will get ddt of, so from equation 2 we can write sum over k del L del sk dot del sk dot del qk dot minus del L del sk del qj, sorry, there is a qk here, it is not qk, it is qj, and sum over k equals to 0. So we just use equation 3 and equation 4 to write this del L del qj as like this, and to write del L del qj dot like this. So now this term, this del sk dot del qj dot, it is a constant, it is not dependent on t, and so we can write it like sum over k ddt of del L del sk dot times del sk dot del qj dot minus sum over k del L del sk del sk del qj equals to 0. Now, in one of our previous classes, we proved that this del sk dot del qj dot it equals to del sk del qj. Okay, we already showed it in one of our previous classes, if you can remember. Then we can write this equation as sum over k ddt of del L del sk dot minus sum over minus del L del sk times del sk del qj equals to 0. So now this is a linear transformation, and all the sk and all the qj, they are independent. SKs are independent and QJs, those are also independent, because those are independent generalized coordinates. So in that case, if the summation is 0, that means this term equals to 0. So we will get ddt of del L del sk dot minus del L del sk equals to 0. Okay, there is a yes, yeah, fine. And this L is a function of Q's, but we can always write this L as del our new, so which is a function of S dot and D, and del sk dot minus S dot T del sk equals to 0. Because the Lagrangian, that is same. The functional form is just different, but they are equal. It means Lagrangian or Lagrange's equations of motion are invariant under point transformation. Invariant under point transformation. It's a very useful property of Lagrangian. That's all for today. Tomorrow in the next class, we will talk about what if in our system we have the constants, how we can deal with them. So that will be the topic of our next class.